Welcome back, engineers. Let's talk about the ultimate engineering duo. Think of concrete as a liquid stone. It is a champion at handling massive weights compression, what we call high compressive strength, HC. But here is the catch. Concrete is like glass. It is incredibly brittle. If you try to stretch it or bend it, it snaps instantly because it has almost zero tensile strength. It's a giant with a glass jaw. To build anything that lasts, we need to solve this fatal flaw. Enter the hero, steel. We embed steel rebars as the tendons of our structures. Why steel? Because it brings high tensile strength, Phi, and ductility. But the real magic is their secret bond. First, they share the same coefficient of thermal expansion, meaning they expand and contract at the same rate when the sun hits them. Second, those ribs you see on the rebar. They create a mechanical bond, locking the steel into the concrete so they move as one single unit. When a beam deflects under a load, it's a tale of two zones. The top part shortens, putting it in compression. The bottom part stretches, putting it in tension. Since concrete can't handle stretching, it wants to crack at the bottom immediately. By placing steel at the bottom, we catch those forces. The steel takes the hand of the concrete, holding the crack together and allowing the beam to carry weight that would otherwise destroy it. While in the middle, there is a point where the beam feels no stress at all. We call it the neutral axis. To calculate the beam's bending capacity, engineers use a brilliant shortcut, the Whitney Rectangular Stress Block. Real stress in concrete is a complex curve, but we simplify it into a neat rectangle of depth, A2. We establish equilibrium where the internal compression, C, equals the internal tension. The compression, C, is calculated as 0.85 times FC times the compressed area, while the tension, T, is simply the area of steel times its yield strength. These opposite forces defines the beam's bending capacity. However, there is a rule for how much steel we can use. We can't have too little and we can't have too much. If we have too little, the beam might snap the moment the concrete cracks. But the real danger is too much steel. Over-reinforced? If you pack in too much steel, it won't stretch. Instead, the concrete at the top will explode suddenly without warning. This is a brittle failure, and in engineering, a failure without a warning is a catastrophe. Our goal is always an under-reinforced design. We want the steel to yield and stretch first. Why? Because as the steel is ductile, it can stretch beyond yield without failure. Therefore, the beam sags and large cracks appear. The building is screaming at the occupants to get out. This is ductility. It's the difference between a building that gives you time to run and one that collapses in a split second. We design for life safety by choosing the steel ratio carefully. So, concrete handles the squeeze, and steel handles the stretch. This partnership is the backbone of our modern world. But static loads are only half the story. What happens when our structures face nature's extremes? From the massive seismic forces of an earthquake and the crushing winds of a hurricane, to the relentless heat of expansive soils and the sudden impact of a blast, the math stays the same, but the stakes get much higher. In our next session, we'll see how we push these RC principles to the limit to survive the most hostile environments on Earth. If you found this breakdown helpful, hit the like button and subscribe to join our engineering community. What's the most extreme structural failure you've seen? Let's discuss it in the comments. See the next lesson at Strong Foundation Engineering.